Introduction to rings. Firstly, we will study the definition of rings. So let R be a set with two binary operations called addition and multiplication. Then R is called a ring if it satisfies the following properties. So we have already discussed groups. In case of groups, there was only one binary operation. But in case of rings, there are two binary operations called addition and multiplication. So first property, R with respect to addition forms an abelian group. Means it will satisfy the closure property, associative property, closure, associative, existence of identity, inverse and commutativity. Secondly, with respect to multiplication operation, firstly it should satisfy closure property. Means for all a comma b belongs to R, a into b also belongs to R. Secondly, it should satisfy associativity. For all a, b, c belongs to R, a into b, then it is multiplied by c, or if I multiply b and c first and then it is multiplied by a, it should be same. Thirdly, distributive property. For all a, b, c belongs to R, first a into b plus c is equals to ab plus ac. This is left distributive law, and right distributive law, b plus c into a. This is equal to ba plus ca. So a set which has two binary operations, if with respect to plus it is an abelian group, with respect to multiplication it satisfies closure property, associative property and this distributive property, then we will say that R with respect to addition and multiplication is a ring. Next, commutative ring. A ring R is said to be commutative if AB is equals to BA for all A comma B belongs to R. Next, ring with unity. A ring R is said to be a commutative ring with unity denoted by 1 if whenever it is said unity, then it is with respect to multiplication, means a into 1 is equals to 1 into a for all a belongs to R. Then we will say that this is a ring with unity. Next, units in a ring. Units in a ring simply means multiplicative inverse. Let R be a ring with unity. A is a non-zero element which belongs to this ring R. Then this is called a unit in R if A inverse belongs to ring R. Means any element is called a unit if its inverse also belongs to ring R. The set of units in R is denoted by UR. Note, UR forms a group under multiplication. We have already discussed that UN, the group of units, forms a group under multiplication. Now we will study some examples of ring. First, the set of integers is a commutative ring with unity. Commutative ring with unity, which is 1. And units of integers are 1 and minus 1 only. Is this clear? By units of integers are 1 and minus 1 only.
1 into a inverse से belong कर रहा है ना यूनिट में, ठीक है।
ठीक. Second, Zn for n belongs to Z plus is a commutative ring with unity and units of Zn. These are a belongs to Zn such that GCD of a comma n is equals to 1. This also we have already discussed in case of groups. The same as UN group only. Third, MNR. This is a non-commutative ring. We know that in case of multiplication, commutativity does not hold. With unity. Units of MNR. This is GLNR. Because set of units means A inverse belongs to R. We've already seen that in this n cross n matrices whose entries are real entries, In this case, determinant should be non-zero, na? Then only our inverse will exist. So that's why GLNR is a group of units. Is this clear?
Yes, ma'am.
Rx. This is the set of all polynomials with coefficients from R and indeterminate x. Rx is a commutative ring with unity, and here units of Rx will be the set of all non-zero constant polynomials. The set of all non-zero constant polynomials.
इसमें indeterminate x का मतलब क्या है? Are a set of all polynomials with coefficients from R, ये clear है. And indeterminate
indeterminate x मतलब जब भी हम polynomial लिखते हैं तो उसकी कोई हम वैल्यू तो नहीं पुट कर देते ना. पॉलिनॉमियल अगर मैंने एक्स स्क्वायर प्लस एक्स प्लस वन लिखा तब जाके पॉलिनॉमियल बनता है ना. अगर एक्स की जगह में कोई वैल्यू पुट कर दो तो वो पॉलिनॉमियल तो नहीं रहेगा ना.
तो रिमाइंडर हो जाएगा ना पॉलिनॉमियल. द वैल्यू डिवाइड.
इनडिटर्मिनेट एक्स का यही मतलब है कि ये वेरिएबल फॉर्म में ही रहेगा आपका, कोई आप वैल्यू नहीं पुट कर सकते, तब जाके वो पॉलिनॉमियल रहेगा आपका.
ठीक.
नेक्स्ट C01. This is the set of continuous real valued functions on closed interval 0, 1. Means C01. This is a set of all continuous real valued functions on closed interval 0, 1. Means domain is closed interval 0, 1 and it is real valued. So codomain will be real numbers such that f is continuous. And here operations will be C01 is a commutative ring with unity under pointwise addition and pointwise multiplication of functions. So addition, f plus gx, this is equal to fx plus gx for all x belongs to closed interval 0, 1 and multiplication f into g, this is equal to fx into gx for all x belongs to closed interval 0, 1 and here group of units, set of units will be all the functions which are non-zero, set of all non-zero continuous functions for all x belongs to closed interval 0, 1. Next, what will be a zero ring? Simply R equal to singleton 0. 7th, ring with trivial multiplication. let R with respect to plus be any abelian group define multiplication on R as A into B equal to 0 for all A comma B belongs to R. So it's a commutative ring without unity. Because if it is with unity, then it should be A into 1 is equals to 1 into A. But our multiplication is defined as this. So if I follow this, then A into 1 is equals to 0. ये हो जाएगा ना? तो unity तो हमारे पास नहीं आ पाएगी. Clear हुआ ये? If I follow this defined multiplication, A into B is equals to 0, then for unity I need this A into 1 is equals to 1 into A. If I apply this given multiplication, then A into 1 is equals to 0.
A should be 0 then B should be 0.
तो मल्टीप्लिकेटिव यूनिटी तो नहीं आ पाई ना, क्योंकि मल्टीप्लिकेटिव यूनिटी आपकी 1 हो सकती है, ये 0 नहीं हो सकती. नेक्स्ट, प्रॉपर्टीज ऑफ अ रिंग. Let R be a ring first for A, B, C belongs to R, M and N belongs to integers. First, 0 into A is equals to A into 0 is equals to 0. Second property, A into minus B is equals to minus A into B. This is equal to minus AB. Third, minus A into minus B. This will be AB. Fourth, A into B minus C. Left distributive law, AB minus AC. Right distributive law, B minus C into A, BA minus CA. Fifth property, M into A, N into B. This is equal to Mn into AB. Sixth, M into AB is equals to M into A into B is equals to A into M into B. Associativity होगी. Seventh, N into minus A is equals to minus N into A. Second, if R has a unity, then it is unique. As we have discussed in groups, if group has identity, then it is unique. Next, zero ring is the only ring in which unity is 0, because this zero ring contains only zero element. 0 equal to 1 means unity is 0. ऐसे कंफ्यूज नहीं होना कि 0 इक्वल टू 1 क्यों लिख दिया, वो तो ऑब्वियसली पॉसिबल नहीं है, बट हियर 1 डिनोट्स यूनिटी. नेक्स्ट, idempotent element. Let R be a ring A belongs to R. This is an idempotent if A square is equals to A. So if I have any ring R, A is an element of R, it is called an idempotent element if A square is equals to A. Nilpotent element. Let R be a ring A belongs to R is a nilpotent if there exists smallest n belongs to Z plus such that A to the power n is equals to 0. So these are idempotent and nilpotent. For example, for this nilpotent element, if I take Z2 equal to 0, 1, then in this ring you can clearly observe that 0 square, this is 0, 1 square, one only. This is with respect to multiplication. And if you want to do with respect to addition, then 0 square means 0 plus 0 na? Again it is 0. 1 square means 1 plus 1, this is 2, and addition modulo 2, it will be 0 modulo 2. So this is an idempotent element. Also a ring
तो with respect to addition तो idempotent नहीं होगा ना,
with respect
क्योंकि
to
1 आता है होगा फिर 0 आ रहा है.
हाँ, with respect to multiplication होगा इसमें.
हाँ.
So a ring which contains idempotent element is known as Boolean ring. A ring R is called a Boolean ring if x square is equals to x for all x belongs to ring R. Now next is subring. A non-empty set of ring R is a subring of R if for every A, B belongs to S, first property, A minus B, this should belong to S, second property, A into B, this should belongs to S. If these two properties are satisfied, then we will say that S is a subring of ring R. Now some examples of subring. First, trivial subring. Singleton 0, this is the trivial subring of R. Second, every ring is a subring of itself. Third, for each n belongs to Z plus, nz is a subring of Z. For each n belongs to Z plus, nz is a subring of Z. Means 2z is a subring of Z, 3z is also a subring of Z. Similarly. Next, now we will talk about the subring of 2 cross 2 matrices whose entries are from real numbers. So subring is like this: A0, 0B, such that A comma B belongs to ring R is a subring of M2R. Fifth, the ring of Gaussian integers. Which is denoted by Z iota. So A plus iota B, such that A comma B belongs to R is a subring of complex numbers. एक second. A comma B belongs to integers आएगा ना यहाँ पे. And units of Z iota are 1 minus 1 iota minus iota. Note, if R is a ring with unity, the unity of R and its subring need not be same. Means, if R is a ring with unity 1, then unity of R may not be same as unity of subring S. For example, H is equals to 0 to 4. This is a subring of Z6. Z6 is 0, 1, 2, 3, 4, 5. So basically I have picked all the even numbers as a subring of Z6. Now unity of this H. Here unity is 4. A into 1 is equals to 1 into A. So 0 into 4 is equals to 4 into 0. 4 are satisfied. Then 2 into 4, which is 8, and modulo 6, it will be 2. 4 into 2, again 8, modulo 6, 2. 4 into 4, it is 16, modulo 6, 4. और वापस से दूसरी साइड से करेंगे तो भी 4 into 4 ही रहेगा. So unity is 4. But unity of subring, unity of ring Z6 is 1 na? Unity of Z6 is 1. So if ring has unity 1, then unity of subring can be different also. Next is integral domains. Note, cancellation laws do not hold in an ordinary ring. For example, if I have ring as Z6, 0, 1, 2, so on till 5. So A into B is equals to A into C implies B into B is equals to C. This is cancellation law, na? So if I take A as 2, B as 0 and C as 3. So 2 into 0, which is 0, this is equal to 2 into 3. 2 into 3 is 6, modulo 6, addition modulo 6 obviously, I will get 0. But if cancellation law is satisfied, then this should imply that 0 equal to 3, na? Which is absurd. It is not possible. So cancellation laws do not hold in any ordinary ring. Next is zero divisors. Let R be a ring a non-zero element from this ring R. This is a zero divisor in ring R if there exists a non-zero element from ring R such that A into B is equals to 0. I have picked a non-zero element from ring R. It is called a zero divisor if there exists another non-zero element in ring R such that their multiplication is 0. For example, in Z6, 2 is a zero divisor as 2 into 3. This is 6, addition modulo 6, it will be 0. Second, M2R. Then 0, 1, 0, 0, 1, 0, 0, 0. These are zero divisors. If you will pick any non-zero element from this M2R, for example, if I pick 2, 0, 0, 0, and if I multiply with this 0 1 0 0, then this is equal to 0 1 0 0. एक मिनट, M2R ये वाला एग्जाम्पल तो नहीं चलेगा। अगर 2 0 0 0, ये वाला भी नहीं चलेगा इसके साथ। तो चलो इसको मैं एक बार देखूंगी कि इसमें क्या मल्टीप्लाई करें कि ये ज़ीरो डिवाइज़र बन रहे, जैसे यहाँ पे हमने देखा था, क्योंकि एक एलिमेंट मुझे रिंग आर से पिक करना है और ये मुझे ज़ीरो डिवाइज़र मिल रहा है।
इनको आपस में मल्टीप्लाई करेंगे तो 0 आएगा।
हाँ, आपस में मल्टीप्लाई करके, हाँ, फिर उसने यही कहा है कि इनको आपस में करें, क्योंकि एक नॉन ज़ीरो एलिमेंट हमने पिक कर लिया रिंग आर से, और इसको अगर, हाँ सही कहा, इसको मल्टीप्लाई करा तो 0 0 0 0। ठीक है। नेक्स्ट, इंटीग्रल डोमेन्स। So integral domains is basically a ring which has no zero divisors. Let R be a commutative ring with unity. R is said to be an integral domain if A is a non-zero element which belongs to ring R and A into B is equals to 0 implies B is equals to 0. So in other words, we can say that R has no zero divisors. Now let us see some examples of integral domains. Integers is an integral domain. Ring of Gaussian integers Z iota. This is an integral domain. Third, can you check and tell me whether Z6 is an integral domain or not? Simply you need to pick an element from this Z6 and you need to check this condition whether you are getting this or not.
ये तो नहीं होगा इंटीग्रल डोमेन।
Reason,
अगर हम 2 + 4 लें 6 विद रिस्पेक्ट टू एडिशन तो वो आएगा 0।
मल्टीप्लाई करना है,
हाँ
मल्टीप्लाई करना है, A into B है ना,
A into B करना।
2 into 3 करोगे तो 6 आएगा।
But that is 0, but 2 and 3 are not 0, so 0 divisor तो है ना यहाँ पे।
क्या
2 into 3 करेंगे 6 करेंगे ना, 6 आएगा तो फिर 0 आएगा ना.
हाँ, this
So
means
that means 2 or 3 are 0 divisor.
means it has 0 divisors, so it is not an integral domain.
Hmm.
So ZP is an integral domain if and only if P is prime. Next example. Set of all continuous functions whose domain is 0, 1 and codomain is real numbers. This is not an integral domain because if I define functions as fx is equals to piecewise function 0, 0 less than equal to x less than 1 by 2, x minus 1 by 2, 1 by 2 less than equal to x less than equal to 1, gx, this is equal to 1 by 2 minus x, 0 less than equal to x less than 1 by 2, 0, 1 by 2 less than equal to x less than equal to 1. Now clearly fx is also non-zero, gx is also non-zero, but their product is 0. So it is not an integral domain. Fifth, every subring of an integral domain is an integral domain. Every subring of an integral domain. We know that integers is an integral domain and subring of an integral domain. Subring of integers is of the form nz. This is subring. Subring of an integral domain is an integral domain. So nz is also an integral domain. Note, cancellation properties holds in integral domain. Next, division ring, also known as skew filled. A ring R with unity is said to be a division ring if every non-zero element in R is a unit in R. Means a ring R with unity is said to be a division ring if every non-zero element has a multiplicative inverse. This is the only meaning of unit. Example, integers with respect to addition and multiplication. This is not a division ring. As every element of integers is not unit except +1 and -1, because we have discussed in this definition that every non-zero element is a unit, but in case of integers we have only two units, +1 and -1, so it is not a division ring. Second, q with respect to addition and multiplication and real numbers with respect to addition and multiplication are division rings as every non-zero elements of Q and R are units. Next is field. So field is a commutative division ring is called a field. Means field is a commutative ring and it is also a division ring, means every element has a multiplicative inverse. Now some examples. Rationals, reals, complex numbers, these are fields. Second, Q root D. This is A plus B root D such that A and B are from rational numbers. This is a field if D is a square free integers. Square free integers मतलब स्क्वायर नहीं आ सकता, √4, √16 ये सब नहीं आ सकता इसमें, √25. Third, Z3 iota. This is equal to A plus iota B such that A and B belongs to Z3. This is a field. And also ZP iota. This is a field if and only if P is congruent to 3 mod 4, where P is a prime. Fourth, every field is an integral domain. So field implies integral domain, but converse need not be true. Converse need not be true. Means we know that integers is an integral domain which is not a field. Can you tell me why integers is not a field? फील्ड होने के लिए कॉम्यूटेटिव डिवीजन रिंग होना पड़ेगा.
कम्यूटेटिव डिवीजन भी होना चाहिए और इंटीग्रल डोमेन भी होना चाहिए.
हाँ, मैं वही पूछ रही हूँ कि every field is an integral domain. Converse is not true. Integers is an integral domain, but it is not a field. The reason is because it is not a division ring. Integers is not a division ring, na? Only units were 1 and -1. So if I have finite integral domain, then it is a field. And in case of integral domains, we have discussed this example. Then ZP, this is a finite integral domain. It is an integral domain if and only if P is prime. So result is every finite integral domain is a field. So it can imply that ZP is a field if and only if P is prime. Next, characteristic of a ring. The characteristic of a ring denoted by char R. This is the least positive integer n such that n into x is equals to 0 for all x belongs to real numbers, and if no such integer exists, then characteristic of ring R is equals to 0. Characteristic of Zn will be n, and characteristic of an infinite ring, it will be 0. Now some properties of characteristic are: first, characteristic मतलब ऐसे सोच सकते हो characteristic of a ring R, जैसे ग्रुप में हमने ऑर्डर पढ़ा था, ग्रुप का ऑर्डर, सिमिलरली रिंग का ऑर्डर ना होके करेक्टरिस्टिक होती है, ठीक है. करेक्टरिस्टिक ऑफ अ फाइनाइट रिंग R is finite. Moreover, characteristic of R divides order of R. Secondly, characteristic of an infinite ring need not be 0. There are some exceptions for this. For example, Z3x. This is a polynomial ring whose entries means coefficients of polynomial are from the Z3. So this is an infinite ring with characteristic 3. Third, let R be an integral domain or a field, then characteristic of R is either 0 or P, where P is a prime. Fourth, let R be a ring with unity, then characteristic of ring R depends on additive order of unity. If order of unity is infinite, then characteristic of ring R is 0. If order of unity is finite, then characteristic of ring R is n. Now some extra important properties. First, let R be a finite ring such that R with respect to plus is cyclic, then R is commutative. So R is a finite ring, means it has finite number of elements, such that R with respect to addition is cyclic, means it has some generator which will generate this ring R, then R is commutative. Second, let F be a finite field then order of this finite field will be p to the power n, where p is prime and n is natural number. Third, Let R be a finite commutative ring with unity, then every non-zero element is either a unit or a zero divisor. This is not the case when R is an infinite commutative ring with unity. So if R is a finite commutative ring with unity, then every non-zero element is either a unit or a zero divisor. Fourth, if R is a commutative ring without zero divisors, then every non-zero element in R has the same additive order. Also, there is no integral domain of order 6. ठीक है. After this, next topic is ideals and factor rings. वो फिर हम कल start करते हैं.